So welcome to the fourth day of this bootcamp. And today, the topic will be about TTS and STT, which is text-to-speech and speech-to-text, plus reinforcement learning. Okay. So yeah, TTS stands for text-to-speech and STT for speech-to-text. And these are like the way that a program can maybe have a conversation with someone, like an actual person. So you would recognize his speech first, transfer it into text, and then maybe later using an AI model, formulate a response, and then using the text-to-speech, convert this response into actual audio to interact with the user. Okay. And we will also be using OpenAI Gem and Stable Baselines 3. So OpenAI Gem is a library that contains environments that someone might use to train their reinforcement model. I will show you a lot of types of environments. And then for Stable Baselines 3, it's a library that contains the models themselves for reinforcement learning. So we'll be using these to train the model and then see the result. Okay. So let's jump right in. Let's create a new file. And the first thing I want to show you is Google's text-to-speech. So let's call this, let's say, GTTS try. Okay, so this is a library by Google, and it uses Google's API for text-to-speech. So this requires internet access, cannot be offline. But other than this, it works very well. Like you cannot even notice any delay. The first thing we're gonna do is from GTTS, we will import GTTS, but in capital. That's just another module inside. Okay. And the next thing we want to do is do the actual detection, the actual speech synthesis. So this is easy. It's just using one command. We write the text that we want. And let's make it hard for this model, this AI. Let's do a tongue twister. Sally sells seashells by the seashore. Okay. And then we can save this. Let's save and let's call it Sally. Sally.mp3. So this will generate a Sally.mp3 file, just as easy as this. You can see here. I'm not sure if you can hear. Let me try. Let me know if you can hear this. Can you guys hear anything? If not, I will reshare to make sure. Let me share the screen and make sure that sharing the sound is enabled. Okay. Now you should be able to hear this.
Sally sells seashells by the seashore.
Okay. So we generated this, but it's an MP3. Can we directly play this? And the answer is yes, but we will need another library called PlaySound. So from PlaySound, the library, we will import a function called also PlaySound. Okay. And all we have to do is add PlaySound and then this Sally.mp3. Okay. So what this will do is after saving this, it will play this file. That's all. It's just as easy as this. Super easy. So let's play this.
Sally sells seashells by the seashore.
Nice. Okay. You can pass more parameters. The first one we can pass is the language. So this is English. So let's try to do something else. Let's try French. Okay. And you can also pass accents. So this is the accent, TLD. And let's also make it French. And now let's say something very French. Bonjour. Okay. Let's keep the naming for now, just to hear this.
Bonjour.
You can see, very French. I'm not sure if you guys can hear. Can you guys type something if you can hear? Because this, I'm not sure if Zoom allows you guys to hear. Clear. Okay, nice. So yeah, this is very French.
Bonjour. Bonjour, merci.
Okay. You can keep playing with this. There is Arabic, there is Mandarin, there's ZH for Mandarin, and so on. So you can try different languages later. So this is the first library that you can use to do this. But this requires internet access. So if you're putting this on a robot or on other something else that will be offline in the future, you cannot use this. So instead, there's another library. I'll show you. This time is TTS, but offline. Okay. The library is by TTS X3. This is the library. And this is completely offline. Nothing online. The entire thing can generate the speech locally. The first thing we will do is create an engine. And this is by just initializing this. So our engine, our speech synthesis engine, is just the initialization function for this. And then we can say, or tell the engine to say, engine.say, and then whatever text that we want. Again, let's do the same thing. Just copy it from there. Okay, let's go back to SETI. Okay. Nice. And then we can say engine.run and wait. If we're running this, it will say this and then wait. That's it. So it's
Sally sells seashells by the seashore.
okay. And this you can customize more things than just the accent. So the first thing you can customize is the voice itself. You can use voices if you download like a voice file locally, but it has two default voices. And we can get those. Let's say voices is equal to engine dot get property. And this property is called voice. Okay. I think it's voices. Okay. Voices. Once we got these available voices, we can then say engine.set property. We're setting the voice property to voices has two voices. One is male, which is 0, the default that we just now heard, and the other one 0 is male, and this one is female. And then we have to say like .id. It's ID. Okay. So if we do this now, it should be
Sally sells seashells by the seashore.
That's a female voice. That's the first property that we can access. The second property is the rate, the speaking rate. So we'll do the same. This is not necessary getting the property for the rate, I mean. Well, let's do it anyway. Let's get the rate and then engine.set property. Set the rate to the rate that we just got. Let's store this inside rate. And let's say you want to make it faster. So rate plus 50 maybe. So like it will be faster.
Sally sells seashells by the seashore.
Can make it even faster. 200.
Sally sells seashells by the seashore.
Okay. And you can even make it slower. You can say minus 50.
Sally sells seashells by the seashore.
Okay. Finally, you can also change the volume. Copy and paste this. Volume. This is also volume. You can say set the volume plus something. And this is in like 0 point something, so don't increase too much.
Sally sells seashells by the seashore.
Yeah, and then you can keep increasing.
Sally sells seashells by the seashore.
I don't know if you guys can hear the difference, but okay. It has many properties, and you can also, I think, select the language. Also, language is also a property, one of these properties. But the main advantage of this is it can run offline, so you don't need any internet connection to do this, which is not the case with the Google text-to-speech. But Google has an advantage of having much more languages compared to this one. Okay. So any question about these two modules? It's clear. Nice. Double quote or single, doesn't matter. Can change all of them to double or single. Python takes care of this stuff. Yeah. Nice. Okay. Yeah, as long as you have a stable internet connection, then this one is better. It has a lot of languages. I didn't try with Arabic, but you can try. I don't know how that was turned out. But it basically, do you know like the Google Translate, the voice that says the words there? Yeah, it's this one. So it should have all the languages. Theoretically. Nice. Okay. So if no other questions, we will move on to the other part, which is speech to text. Let's create a new folder. Let's call this STT. Okay. So the module is speech recognition. This one. Let's import it as SR for short. Otherwise, we'll have to type in speech recognition every time, which is very long. Okay, so the first thing we want to do is define our recognizer. So the recognizer is just sr.recognizer, as easy as that. The second thing we want to do is the source, define the source. So this can either be an audio file or it can be your mic, your microphone. So let's try with a file first. sr.audio file. Oops. New file. And then I already have one called audio.wave. Okay. And then you'll do with audio as source, as the source basically. Oh, not this one. Okay. As source. Let's say record is rec, the recognizer that we just defined, dot record. So it's like we're recording the voice again, but this time we will pass it through the recognizer. Okay. And then we have it as an object as record. Finally, with this done, you can say that the results will be equal to recognizer dot. So there's a lot of recognize engines. The most common one is recognize Google. There's recognize Bing, Azure, Amazon, IBM, TensorFlow, a lot of companies. But the most commonly used one is Google. And of course, this requires internet connection, this speech recognition thing, since we're using their libraries. Okay. And we will pass the record value that we just defined. And this should give us the results. Then we can print the results. Let me play the audio file first, so you know what's being said. It doesn't make any sense. Just a warning. It's just some guy talking about something.
But what if somebody decides to break it? Be careful that you keep adequate coverage, but look for places to save money.
Maybe it's taking longer to get things squared away.
Okay. This is the audio file, and you can see it has a bit of noise, which is nice to test the capabilities of this recognizer. So let's see if it outputs the same stuff. Oh, okay. I didn't pass the source here. Source, which is the source. Take some time, and then outputs. But what if somebody decides to break it? Be careful that you keep adequate coverage, but look for places to save money. Maybe it's taking too long to get things square, and it didn't catch away, I guess.
Get things squared away.
Squared away, but it just got square. That's fine.
But what if somebody decides to break it? Be careful that you keep adequate coverage, but look for places to save money.
Maybe it's taking longer to get things squared away.
Okay, so it's pretty accurate. It did get the all the text. Very nice. We have now an auto subtitle machine. And this is if you want to use an audio file. I can send this audio file. Sure. Okay. I sent the audio. Okay. So that's nice if you want to transcribe an audio file, if you have an audio file, and then you want to get like these subtitles for any reason, you can do this. Okay. But realistically, people use this to put on like Google Pixel machines and so on and so on to recognize what you're saying and then do something, which is nice. There is one more function. You can actually adjust. It's called adjust for ambient noise, which basically removes the noise, like the background noise, from your detection, from your source, so that you have a smoother detection. For this one, it's not needed, but just in case you have a more noisy audio file, you can use the source instead. So it's just, if you pass it through this, it will try to remove the noise. It will output the same thing. But now you can see it got the ED squared, not just square. Okay. It code a little bit more when we adjust it for ambient noise. Nice. This is if you want to use an audio file. But if you want to use the microphone, okay. So for the microphone, there's another function. Mic, let's say, is equal to sorry.microphone. Okay. And this one will be mic instead as the source. And we will listen, not record. So this will be listen. Listen to the source. And then we can set a timeout, like listen for 5 seconds. That's it. And then try to interpret this. I cannot try this because I'm using my microphone now, but you guys can try it. And this you have to define the index of the microphone. So 0 is your default microphone on your device. 1 is the second microphone, and so on. Same as the OpenCV library with webcams. So if you want to use your microphone to detect this is the code you use. It's simple. It's almost the same. Just instead of an audio file, we have a microphone now. Great. Any questions about this? You can try the other. Let's try something else. Let's see Bing. See if they are even close to Google's detection. Oh, wait, I'm still using the microphone. Let me turn this back to audio, this to record. Okay. Nice. Apparently, Bing requires something else. Key, language, and then something. Okay, sure. No one uses Bing anyway. With Google, you can also define the language. There's also key, but the default is none. Language, and then you can select English, United States, and so on. Let's go back to Bing and try to say none. Key is none. None. Must be a string. Okay. Not worth it. Not using Bing. There was Google Cloud. What is this? Requires credentials. Okay. Never mind. Just stick to the normal Google. Text to speech. Can try later the others if you can get them to work. But yeah. Any questions regarding this? Do they all need internet connection? Yeah. For this one, for this library, it uses internet connection. So yeah, all the methods use internet connection. My VS Code for some reason is not showing the required arguments preview as it does for you. Even some methods aren't color coded as if they are unrecognized, but the code works fine. Any idea why is that? You might need to install one of the extensions here called Bylance. This Bylance extension helps with the autocomplete and like highlighting and stuff. Oh, you have both installed, so there should be no other no other reason. I'm not sure, but VS Code sometimes like is weird. I will search online. If I find something, I'll send you. Yeah, try that. Okay. Okay. Any other questions? Okay. If no other questions, we'll go to the main part for today, or the most difficult part, but that will take time. Reinforcement learning. Okay. So I want to like give you an overview about reinforcement learning before we start this. So this is the library that we'll be using for the training, which is called stable baselines. And it has like a set of reinforcement learning algorithms. A to C, which is short for actor advantage critic, something like this. There's also asynchronous advantage actor critic. And there are different types for data. So basically what will happen is we have an environment which will be supplied by this gymnasium library, which is basically just has a lot of environments for reinforcement learning. One of them is this. If you go here, there are classic control environments, something like this card ball, and then you're trying to balance it and so on. There are some game environments, might be the Walker, car racing, so on. Some other weird environments. These environments are cool, the Mujuku environments. It's like 3D learning. teaching stuff to walk or to crawl, I guess, for the swimmer. And then there is the Atari environments, which we will be using today. It has like almost every Atari game you've played before. For today, I chose Frogger. I'm sure everyone played Frogger before. This guy, this frog, trying to cross the street. Okay. And we'll try to use reinforcement learning to make this guy cross to the other side successfully. And we will be doing our own environments, but without the GUI, because the the thing you can use later is writing your own custom environment and then using these models by stable baseline to train it for you, so you don't have to actually develop a model from scratch or something. Okay. So, okay. So what's gonna happen is basically we have an environment that gives us some sort of observation. The observation for this is the image. Every pixel here is the observation. This is the input to our reinforcement learning model. So every pixel in this is passed to the reinforcement learning model. And then the output is going to be actions. So you have like these set of actions, which is no operation, up, right, left, and down. This is what the model can make the frog do. And this is the output of our model, of our reinforcement model. And then there's also rewards. I don't know if we passed by rewards. But rewards are basically the incentive that the reinforcement learning model gets. So it would be something like the further you get, every pixel you get from the end, you get more rewards, something like this. Okay. So how it works is just it takes the observation, the number of pixels, and then does something, does an action. At first, this action is random and gets back the reward depending on this action. And then tries to correlate the different states with the output reward depending on the output report. And then when I was in this state, when the pixels were this, and I did this action, the reward was high, maybe, or the reward was low. And then it tries to figure out the connection using the reinforcement model. Each one of these has their own way of doing this. Some are for, okay, there are these discrete, box, multi-discrete, and so on. Discrete means that the actions or the observations are like whole numbers, are like integers, either be this or this or this. And box, the type box, means that it is a float, basically. So the actions are not like 1 or 0, do this or front or right or left like this one, but it would be something like a value, like the speed of something or the position of something will be a float value. So these are the main two types. The others are like multi, it's like an array of this and an array of this and so on, and they're not really used. So depending on these types, the types of observation space you have and the actions you have. For example, for this one, you can see the action space is discrete and we have 5 actions possible, no operation, and then up, down, left, right. And the observation space is a box, so it has like float values from 0 to 255. And then this is the shape basically of the thing, the width and the height, and then 3 is for the RGB because we're inputting the image. Okay. So we'll also use these types later to create our own custom environment. That's why I'm explaining this. And other than this, we can go ahead and jump right in. Any question about this so far, about just the theory of reinforcement learning or the types that I just now explained and so on? Yeah, sure. Which part exactly? Everything? Basically, we're trying to do a reinforcement model for this game. And what we'll do for this game can be applied for all the other environments and custom environments that we will do later. we'll do one custom environment. And this is useful because when you do it in this format, you can use this library, stable baselines library, to do the training for you, to do the reinforcement training for you. All you have to do is pass in the observation and take their actions that this model outputs. And that's all you need. You can see this is an example and so on. And there are different types of algorithms. Today we'll use mainly A to C, which is like advantage, actor, critic. One other popular one is DQN. It's like deep Q network, yeah, based on a Q learning algorithm previously, but this is like the deep version using machine learning and stuff. But yeah, we will be using these to train the model here, and then we get something that plays itself, hopefully, hopefully. And then this can be applied later with custom environments that you can do to like any project that you want. All you have to do is write the environment that you want, and then take this output and apply it to something in real life. Then you have a reinforcement model actually controlling something or doing something. Okay. And the concept of reinforcement learning in itself, yeah, it's better to see to understand better. But I just wanted to introduce you guys to the concept of reinforcement learning, because we will be doing like just taking observations, and then based on these observations, the model will do an action and then see what the reward is for this action. If the reward is high, then okay, we want this combo. We want in this state do this action. Otherwise, if the reward is low, then you don't want this. When you do this state, we give this a low score, give this action a low score, so it doesn't happen again. Okay, just as long as you understand this loop, the reinforcement learning loop should be okay. So let's go back to the code and let's create a new file. Let's call this RL, short for reinforcement learning.py. Okay. The first thing to do is to import Gymnasium, which is the library that I just showed. And then let's say gem for short, import Gymnasium as gem. And we will also import from stable baselines. Okay, let's say from stable baselines, import A to C, which is the model that we will use. And the first thing we have to do is create the environment. So let's say environment equals gym.make. So this receives a string, and this string will be the name of the environment here in this documentation. So for Frogger, it will be this, which is, yeah, gymnasium.make, and then this. If you go back, okay, ALE, which is like Atari logical emulator or something like this, and then Frogger version 5. And then in order to see, let's set the render mode to human, because we are humans, so that we can see. Okay, so that's the first step. The second step is to define the model, which in this case will be A to C. And then you have to pass something called the policy. So there are different types of policies, but the default one is MLP policy. Instead, we'll be using the CNN policy, which is the same as CNN if you've heard before, convolutional neural networks. And it's using this to learn, basically. Okay, that's the first thing. The second thing is the environment. We'll pass the environment itself. And lastly, we want it to output, so we set verbose to 1. So we can see the output of the training and so on. Nice. So now we have the environment, we have the model. I don't want to train the model now. So let's try to do like random inputs and see how it performs at the beginning, just random inputs. So to do this, let's say first we want to do a loop for I in range, let's say 500, just 500. play the game 500 times. And then we want to reset this environment. This will return to stuff, environment.reset, which is like reset the frog to the initial position and so on. And it returns two things, info about this reset and the observation. So ops is short for observation. Okay. And something else, we want to initialize done as false, which is like, is he done? And done only occurs when the frog gets run over. So we have to reset, okay? And then let's say while not done, why it's not done. The first thing we want to do is get the action. So action, and then there's also the state. State is equal to model that we have not yet trained, dot predict based on the observation that we just got, the first observation. So it's going to predict the action to do, and it's not yet trained, so it's probably be random. Okay. And then the second thing we want to do is to actually make the environment step. It's called, okay, so let's type in the stuff that it receives first. So the first thing is it receives the rewards, if I'm not mistaken. Let me check. I receives another observation first, another observation, then the reward, and then whether it's done or not, and then something else called truncated, whether it's truncated or not, if that makes sense. And finally, all of this is the output of a function called step, which just takes step inside the environment, and we pass it the action that we want to take. Okay. So what this loop does is gets the model to predict something, predict an action based on the observation, which is here, or later will be from here, and then take a step based on this action in the environment, either move up, left, right, down, and so on. And this step will return a new observation, the new state of stuff, will return the rewards in case you want to display the rewards. It will display whether it's done or not, whether the frog is dead or not. Truncated is like, is it stuck or something like this? Usually not used, but we just have to keep it here because it returns five objects. And then info about the current state in case the environment has any info. We don't really care about all this for now, but this is just what you need for it to work. We can go ahead and start. So now we have a model that has not been trained and should now just do random actions, basically. So if I run this, it should open the Atari environment. This is our frog. And it should, okay, this is the starting animation until this guy goes over. Now we start. You can see it does random actions, immediately gets run over. Just doing random stuff now. Also gets run over. Okay. And it will keep doing this and so on. Once this guy passes, game starts, doing random stuff. Oh, this was actually close. Anyway, you get the idea. Yeah. There are other environments you can try, but it's for now, try to make this one learn. Any questions so far before we start the learning? Any questions? Are you able to run this and get the frog running? Yeah, and we're using the last line is just outputs. But this is like stepping the thing, and then also taking the observation that will be used to predict later on and so on. This. So this outputs does the action, outputs the observation that will be used to predict the action again, and so on. The rest are not used unless you want to print them. Yeah, sure, I can send the file. Okay. There is the order of actions to be done. Also, where does it out? It doesn't just stores it. What does it exactly? Okay, this step function, what it does is this is initialized with render mode human. Should be a HUMAN. For the observation for this one, it does an action. So imagine that the game is paused until you receive the next action. Then when you receive the action from the model, it steps like does one step in the game and then pauses again. So it does this action and pauses. Once it does this action, okay, I want now the current image, the current pixels of the screen. So this is the observation that it returns. And then it also returns the rewards based on this action. Okay, is this position good? Did this position is it encouraged or not? So these are the rewards. It calculates all of this and then returns them. For now, we're not using them because we're not training the model, but later we will run a function to train the model, and then it will actively use the rewards and the done behavior and everything. But for now, we're just taking the action into the environment, and we take this observation, pass it to the model. Okay, here's the observation. Try to give me the correct action, and so on. This loop continues. Opens and closes immediately. Not sure. Is your range correct? Do you have like one in the range or something? Data can be shown in like numbers and stuff. Yeah, you can print everything. For this observation, it's not gonna be really data because it's the image, the pixel image. It's going to be an image. Maybe you can display it using OpenCV, but it'll be just the frame that we saw just now. And then for the rewards, it will be the actual rewards. You can try to print the rewards. It will be like values, either positive or negative, depending on the position of the frog. Let me see, try 0 for now, because it has not yet started. Nothing is happening. This guy goes off screen. Okay, you can see 1, 0 again, 0. Every time it steps closer to the end, it gets 1 reward, and so on. So yeah, that's the environment. All of this is already defined inside the environment, like how much reward to give, what are the available actions, and so on. But later we will write our own environment, then I think it will be clearer what each function does. Okay, so it opens and closes immediately. You can try the code that I sent, and then does it give any error when it closes? Like, do you have any error? You can also try other fun environments, not just Frogger. There is, I think, Breakout is also a classic. This thing where like tries to hit this LE Breakout. This is breakout. Okay, nice. Actually logged out. Oh, so it's doing random movements now. It's moving left and right. But yeah, if we train this, then maybe it can go to the correct position every time to get the ball. Also, the same gets the entire screen as the pixel input, and the output is just left and right. Okay. It will store. We can save the model and then load the model and so on. And yeah, you don't have to store the observation. It's not the observation, it's like uh, the model itself, the learned model. Yeah, and you can save the learned model and then use this learned model later. A lot of people, for robotics at least, they will do a simulation, a 3D simulation of the stuff that they want, train the RL model there, save this model, and then try to apply it on the actual hardware. So they don't train on the actual hardware because this is costly. So yeah. Any other question? Okay. If not, imagine how computer diff is done maybe. Oh, difficulty. Maybe, but I don't think because reinforcement learning is very uh recent. So maybe in older games, probably not. This is not how they do this. But in older games, that might be the case. Some older games are beginning to implement reinforcement learning, so their NPCs are like much smarter. Yeah. So let's do learning now. Let's make this learn something. For learning, we don't need this loop. This we just need to apply the model. For learning, all we have to do is say model.learn and then pass it the number of time steps that we want it to learn. And for this, I think uh, let's say let's just set the time steps first. Let's give it 5,000. Okay. The rate is not gonna be super fast, but we can start typing our custom environment while this trains. And I think for 5,000, even the results won't be that good, but let's try. So we will make the model learn. This is inside there's a while loop and keep learning and stuff. After this is done, let's save this. And let's call this A2C, which is the policy that we're using, the model. And then let's say Frogger, for example, A2C Frogger. And this will save the model. Now if we try, keep in mind that this render mode is human is still on. But if we try to run this, it will train, but it will be very slow because it's like showing us the screen and so on. Waiting. This is very slow if you're training the model. So we will disable this preview. So now it's training. But we'll disable this preview so it can train much faster without having the constraint of showing the pixels and so on. So let's close this. And this time, the render mode is going to be RGB array. So now it's going to train, but it's not gonna show the screen. Okay, and we can track the training progress here. After like 5 or so steps, or I think 500 time steps, it will show here a box. Yeah, this box. We have the episode reward mean, 17, average the reward. The length was 310. This is the FPS, the invisible FPS. Total time steps for now is 1,000. The maximum we said is 5,000. We have the policy loss and the value loss, which is like our loss functions. And we have the learning rate, which at the beginning will be like this, and then will decrease even more. And yeah, that's all. It keeps training. And then later, when it finishes training, we can load this model using this saved one and try to use it and see if there's any improvement. And then we can train it more by loading and then training more, and then saving it, and so on. While it's training for a while, let's create our own custom environment. So the environment that I planned is a shower environment. So let's call it shower to party. So the idea behind this is that there is a shower, someone is showering, and we're trying to control the temperature for the shower, and it starts at maybe like a random value around 38, something like this. And the model has to try to keep this temperature within 37 to 39, this range. Okay. So let's import gymnasium as gym. And our environment is going to be a class. So class shower environment, for example. Oh, okay. The training is done. Let's see this first. So the 5,000 time steps were done. This might be too little, like not enough, but let's see anyway. So the model is going to be equal to A to C, which is the policy to load. And then we will load the name of our model, which is A to C Frogger. Okay. We also have to pass the environment. Environment equals environment. Yeah. And we don't need all of this because now we're just loading the model. Make the environment, load the model, and then let's make predictions based on this model. Let's see if 5,000 time steps were enough to see a visible change in the behavior of this frog. And let's set this back to human so we can see. Let's see. Okay, let's wait for the starting frog here to disappear. Okay, immediately plunges to its death, but oh, very big improvement. It kind of passes the first area. Okay, it fails multiple times, but at least now it reaches somewhere around half the screen. And then, okay, died again, died again. Seems that it's not very consistent. We've only trained for 5,000 time steps, and this was pretty fast. People train up to like 200,000 time steps and so on to get like some consistent behavior. But even this is very nice for now for only 5,000 time steps. So you can play around, you can train it for more. And this is just using CPU, so you don't really need a very strong GPU to train this. So let's go back to our custom environment, the shower environment, and let's try to do this and train our shower environment. Let's close this for now. Good job, Frogger, I guess. And let's go back here. Any question about this, by the way? Loading and saving models using this model just now? Is your model the same as mine? Probably not. It depends on the actions that the model took at the beginning. Yeah, it's not the same, probably. Depends on the action that the model took at the start and then like what it does next. If it maybe turned to the right at the start and then show that this is nice, this gives me rewards, it will keep doing this. Not completely unique, but somewhat unique. But the conversions at the end, if we both train for a very long time, it should reach the same area or the same performance at least. Okay. Nice. So let's go back to this environment. So we're declaring a class called shower environment, and we have to pass the parent of this class is the gym environments. because we're doing something with their own type. The first function, of course, has to be init. Already defines the super for us, which is important in this case. We want the stuff inside the gem environment. And then there are two main variables that we have to define. The first one is action space. So these are the possible actions that we can take. For this shower, there are three possible actions. Either we want to increase the temperature, or decrease the temperature, or do nothing, keep the temperature as is. Okay, so these are our actions. So we can define this by saying gem.spaces.discrete and then 3. So this 3 is the actions, 3 actions, and discrete because it's like we're not increasing an amount, we're just increasing by 1 or decreasing by 1 or 0, nothing. It's not like a float value, so it's discrete. The second thing is the observation space. So self.observation space. And this is going to be the temperature that we're reading, the shower temperature. And this will be floating points, of course. So we'll use the box data type, box. And we have to pass multiple stuff for the box. We have to pass the lowest point, which let's say is 10 maybe, or like 5 degrees. If you're below 5 degrees Celsius in the shower, you're freezing. And then the maximum, let's say, is 50 degrees Celsius, which is very high also. I don't think anyone would do this. So, okay, that's it. The next is the shape. Since we have just one value, so this will just be 1 comma nothing. If this was like a 2-dimensional array, it would be like 1, 2 or something, and so on. Okay. And then finally, we can set the data type. But for now, I think the default is float, so that's okay. Nice. So we have the action space and the observation space. The next thing we want is the state. Let's define our state. It's not like actually here, but the state, what we mean is the temperature. So let's call it temperature, just to be clear. Self.temperature. And then let's say it starts at 38 and then plus a random number. So let's import Python's random. This is a standard library. You could have it without installing anything. It's random. Random. And then the function is called uniform, which gives a floating, like a number between two floating numbers. And let's say between -2 and +2. So it starts at either 36 or like 40 degrees Celsius. Okay. And then let's define something else called the shower length, because we want this to end at some point. We don't want this to like keep going forever. So let's set it to like 120 seconds or 120 steps. This will be like our done. This will be our frog dying. It will automatically die after 120 steps. Okay. I think that should be all for the initialization. The second function we want to do is the reset function. Okay. So the reset is like return everything to normal. So self.shower-length will return to 120. And temperature will return to this. Okay. And we also have to return the observation and info. Same stuff that we're receiving here. If you say environment reset here, turning an observation and info. So the observation in our case is the temperature. And info can just be empty. So info is a dictionary. And we can just leave it empty. So something info. That's fine. For the temperature, for the state, which is the temperature, let's say that state equals. And the thing about this library that the thing has to be in a NumPy array for some reason. And I've not explained NumPy to you guys yet. But basically it's just an array library. This is handles like matrix multiplications and stuff in Python. You don't have to really know much other than that it just handles multi-dimensional arrays. Does multiplications and stuff very quickly. But we won't really be doing any multiplications or any of this. We just want to use it to like transform this temperature into an array. So it'll be like this so far. So we made like a mini list with only the temperature, and we're passing this mb.array to create a NumPy array from this list. And this is our state. So that's all. Let's back the state. We have to do this because the stable baselines library, the way their models work is they are expecting a NumPy array. That's why we will change to this NumPy array. Okay. So this is the reset function done. Finally, we have the step function, which is the function that is supposed to take the action. Have the action passed. Okay, so this will have most of the logic. Let's delete this. The first thing we want to do is decrease the shower length. Once the action is complete, let's make the shower length minus equal 1. Okay, one step has passed. And we'll check later if it's equal to 0 or not, then it will be done. Let's start done equals false at the beginning. False. And then if shower length is less than or equal to 0, then done is equal to true. Change this to true. Okay, nice. This is our done mechanism. Done. The second thing we have to do is take the action. So we'll get our temperature, self.temperature. Then we'll plus equal the action, which is, so we defined it as 3, right? 3 steps. So it can be either 0, 1, or 2. These are the possible actions, possible states. So when we add action minus 1, so we're saying that if it's 2, it will add 1. If it's 1, it will add 0, nothing, which is whole. And if it's 0, it will add -1, which is decrease the temperature. Okay, so this is why we're minusing 1. And yeah, so now we have the action. Let's do the rewards. So we will want to reward this every time that it stays, every step that it stays between 37 and 39, the temperature stays in this region. So let's start the reward as 0. And let's say if self.temperature is greater than 37 and self.temperature is less than 39. Let's do or equal to, equal, or equal. If that's the case, reward is equal to 1. Else, any other thing, the reward will be equal to -1. We don't want that. None of that here. Okay. Nice. Now we have to just do the returns. So we'll do the same that we did here, which is state is equal to this NumPy array. And let's take info2 because this requires info. And let's return multiple stuff. The first thing being the state, which is the observation. Second is the reward. Third is done or not. False. The third one is just truncated. So let's just say truncated equals nothing also. Nothing. Okay. And let me just make sure that I did this. Nothing. Okay, let's make it false instead of false. Truncated is equal to false. Because I think this this output should be false. Yeah, a Boolean, so it's not a dictionary, so false. Okay. And then finally the info dictionary. Okay, that's it. That's all we need to pass back. We're not using this truncated or info, but the rest, the state is the temperature. The word is either 1 or -1. And done is when the shower ends. Okay. There's one more function that we have to add just for like the library's sake, which is render. So to render. And we're not using it, so just pass. This will have like, if we were doing any like GUI to show this shower and the temperature and so on, we would write the code here, but we don't have any of this. So nice. That's all we need. So this is basically our environment. Set 0 here, here too. Any question about this environment? I think it might have been maybe a little bit overwhelming. Indeed it is, yeah. So let me recap just so you can get the whole idea. There are 4 functions that we need to implement to have a successful environment, just like the ones that Jim here like makes, just like the frog just now. These functions being the initialization, reset, step, and render. Yeah, of course, needs some messing with to get used to. Indeed. And for this action space, we have 3 possible actions: increase, decrease, or do nothing. So this is a discrete one, a discrete action space that has 3 actions. For the observation space, we have a value between 5 and 50, and then it's only one value, so just 1, no other parts of the array. And for the temperature, we are initializing at 38 and then adding a random number between -2 and 2. And finally, the shower length is set to 120 steps. Okay. Then we have the reset function. So the reset function is just every time the shower is done, the environment is done, we want to like reset everything. So we set back the shower to 120 and we set back the temperature to 38 plus something random. And this is just returning the temperature in the way that the library prefers. So never mind this for now. Okay, and our step function like takes the action. So this decreases the shower length by 1. And then if it's already 0, then we're done. We're done with this instance. Then repeat again from the start. And then we're adding the action. So we did -1 because the action will be 0, 1, or 2. So now if we -1, it will be -1, 0, or 1. Okay. And then based on the temperature, if it's within this range, we will get a positive reward of 1. Otherwise, it will be a -1. And then this is just returning the stuff. This is just the main logic. This is returning the stuff. No, it's not the max temperature. It's the maximum steps, the number of steps, the number of times that this step function will occur. Because we can't set it to something like this. Like when the temperature increases a certain thing or decreases below a certain value, then we reset. But the thing is, there is no guarantee that it will do this. But we guarantee that after 120 steps, it will reset the shower length to this. There's no like a specific way to define the ending for this shower case. For other cases, you can define whatever ending you want. It doesn't really matter for the learning, as long as it takes rewards when it does the stuff that you want it to do, and maybe negative rewards when it does the opposite. It should be good. Otherwise, the resetting, mechanism is not really important for this. Yeah, it's like the 500 in Frogger. After 120 steps, reset, just reset. Yeah. But for Frogger, is like this 500 is even above the done. So it's like 500, and then this will do for 120, reset. So this is now 499. Does this for 120, reset for 98, and so on. This is just like repeat this entire thing for 500 times. But okay. Any other questions? Finally, this render function. And if we had like a GUI like the frog or something, then we would do this here using any of the Python's GUI libraries, maybe Pygame for doing games and stuff. We could do this here, but this is too much for one day. So let's just leave this empty. Instead, we will be printing like the temperature here, just to make sure that it is working outside here, the observation. So yeah, should be fine. I will send this in the group so you guys can play around with this. But let me check first by running before I send this in case something is wrong. So the way we are importing this here is instead of this, okay, just comment this and let's say environment is now equal to, and we will import from our other file, the shower. So let's say from shower import shower environment. And all we have to do is say that this environment is equal to shower environment. That's it. And we will not load the Frogger model, start a new model, and let's see what it does initially. So just use this new model, fish model, and let's print the observation to see the temperature, like what's it's doing with the temperature. And this is going to be very fast. I'm warning you now, it'll be like a lot of temperatures, but let's see. Hopefully the environment is okay. Otherwise it will throw an error here. Okay, there is an error. Vector normalize. We should use the net scenario images in the box. Oh, okay. We need to change the policy, the CNN policy, which is usually for like images, not for this. The other policy is MLP policy for this, usually. It listed just now. Yeah, there's CNN policy, there's MLP policy, and multi-input policy. But usually, if it's not images, we use the MLP policy. Okay. This was not a problem in the environment. So it's just the choice of the model. Okay, it works. You can see that the temperatures are like not really staying within. So sometimes goes to 40, 20. I see some 20s. It's very fast, but yeah, you can see. So let's train this model using our environment now. So let's learn 5,000 is okay. And I think we will increase more because this model will run much faster than the previous model. Also, nice tip, in Python, the underscore doesn't affect the number, but it makes it much easier to read. So you can see this is still 50,000 for Python, but like you can read it easier. Never mind. Okay, so let's change this to A to C shower. It's another model. Let's save this. Okay. So now we will train, and let's let it train for this 50,000 time steps, but it will be much faster because we're not rendering anything at all. There's no images. We'll see now. Okay, something is wrong. Seed. Okay. Usually there's another argument here called seed, but we don't really need it here. It's like the random seed, so it makes sure that it's randomized, but we don't care for now. Okay, nice. It's training, and you can see it's very fast. It's like 3,000, 3,500, 5,000. It already reached 5,000. Would have ended here, but okay. And you can see the FPS is like 910. A lot of FPS. That is a lot. You can see the error is decreasing gradually. Oh, it's in ease now, and so on. Okay. So 50,000 steps should be done in no time. And then we'll see if it can more accurately make the shower temperature stay within this range. And then we would have successfully created our own environment. And this can be applied in an actual environment if you have like an Arduino, and then you connect this to a temperature sensor and also controls the temperature of the shower somehow. I don't know, servo motor rotating the knob. And then you send all these readings to Python, and it just takes these observations, sends to the Arduino whether to increase or decrease the temperature by 1 or do nothing. And you have like made your first reinforcement learning actual project, actual physical project. Then you write the paper, everything's good. Okay, so now we have this A2C shower model. Let's load this model, A2C shower, and see if it's effective and keeping the temperature within the range. Let's go. Okay, so it's not really effective yet. You can see that's very, if I try to control C this, 97, 101. These are very high temperatures. Seems like it favors going to the extreme. So it might need some more training. And just in case, let's see if there's something wrong, if the rewards are correct or wrong. Let's run this again. I want to make sure that it's giving -1 for each of these. Yep, so many -1s. Yeah, still it has not learned anything. Let's make it a bit easier for the environment. Let's make this one, just random by 1. So it will still be inside the range at least once. So it knows where the correct range is. And let's retrain this time. I won't load, I will just retrain from 0 because it might have learned something wrong at the beginning. This way I know that it did not. Okay, so what might have happened for this is that it starts at 40, let's say, or at something less, and then it doesn't get a chance to stay within this one region, so it doesn't know where the one region is. All it sees for the rewards is like -1, so it just keeps going forever, searching for this one, for the reward of 1. And I realized I changed it only for 1. I should have changed it here too, but okay. Let's see if this is any better. Then we can retrain again. Okay, it's done. Let's see if this is any better. Even though like we should have changed the other one too. Let's see if this affects anything. If this training this time is better. Okay, still not better. But at least it's keeping it around 60, no 100s this time. Let's fix this here, also to 1 and 1. This start at least at the correct range. And maybe we can increase the number of times that it trains. Because it's training very fast. Let's say 100,000. Easy. Should be done in no time with 900 something FPS. Yeah. Any questions while it's training? In general, so far about the entire thing? No questions. The environments here are interesting though, but for most of them, they like require to install third-party software. For this, you have to install like the physics engine, this Mojoko physics engine. Otherwise, I would have chosen this because it's just too cool, man. Look at this. Unbelievable. The classic control stuff is kind of boring. This resets way too early. I want to see this like swing more. And this pendulum is trying to make the pendulum like stand upright. But the Atari is classic because the first paper that used deep learning for reinforcement learning, oh, the study was actually done on Atari games, and it's a classic. And it just started this deep learning thing all over the world. Some guy decided to play some games using reinforcement learning, deep reinforcement learning, and this was the start. There's so many games to try, and yeah, you can try all of these. You can play with all of these. Let's see, okay, almost done. Okay, done. Nice. Let's hope this time can actually keep the temperature within the range. Oh, damn. Okay. This is very, very like 37, 38, 37, 38 is keeping the temperature, and it's always getting this sweet reward of 1. So we've made our control system using reinforcement learning. Okay. So nice. Any questions? This is all I have for today. So if I have any questions overall or anything to say, you can just say it. Otherwise, I think we can end. Anything you're curious about? If not, should be ending right now. Okay. The attendance link has been sent inside the meeting chat. So make sure you fill the attendance. And if you have any feedback, please type the feedback inside the feedback box. Yeah. Yeah, it's AI. It's deep neural networks. You can study more about the exact, like how it exactly works if you want. I can maybe send the paper that used this at Terry, the first paper, to the group if anyone is interested. And there is reinforcement learning without using deep neural network, without requiring training and so on. And it's called Q learning or SARSA. These are the algorithms that do not require any neural networks or anything. It's just pure algorithm. And it's not that hard. I have personally implemented Q learning, and it's nice. And it's nice to understand this, how this works, because deep Q network is just Q learning, but using deep neural networks. So it's nice. I might send something about this also on the group later. Okay. If that's all, let me just share. Yeah, exactly. Yeah, we can make up a game, the rules and everything, and then teach the AI how to play this. Yeah. The GUI can be done using another Python library. I recommend using Pygame. It's a Python library for doing games, for making games, and it's super easy to create like games using Pygame. So that would be a nice choice. Otherwise, you can link it to something like even outside. Doesn't have to be a game. Like can be applied in actual real life. You can get maybe observations from an Arduino. There's a library called PySerial, so you can send using serial the data from the Arduino, and then the laptop or any other, maybe a Raspberry Pi, receives this serial data as the observation, then outputs an action to the Arduino, sends something to the Arduino, and so on. And you can do all this. Yeah. In a project, if it requires Python, then yeah, sure. Because you're not really using Python on an Arduino. Yeah, you're not really using Python in the Arduino. You're just sending serial information from the Arduino. So all the code inside the Arduino is in C++. You just send using the print function to the USB, and then your computer receives this USB through a library called PySerial, reads whatever your Arduino sends. Then all the code on the laptop is in Python, sends back using also PySerial using the USB to the Arduino. Arduino also reads it using the normal read line function inside the Arduino, and so on. So everything on the Arduino is C++, and everything on the PC or the high-level controller is in Python. Just the communication is in serial communication. Yeah, this is how you can make something like this work. Okay. Sensor libraries in Python. There are some sensor libraries in Python, but these are for like LiDAR or something like this. It's not really for lower level stuff. Yeah, there is no that. Python is not used on the Arduino. The only microcontroller that uses Python is the new Raspberry Pi Pico, and it's not using even Python. It's like MicroPython, something like this. Yeah. Yeah, they're just different learning algorithms. One more very popular one is PPO, Proximal Policy Optimization. Also is very popular. These are like the main three: A2C, PPO, DQN. DTPG is also popular. It's like DQN, but you can have like box actions. So MicroPython is like Python, but it can run on a microcontroller. It's like a simplified version of the Python. Yeah, sure. I will send you the link to all of this. I'll send this. This is, let's just go to the screen here. Solution. Okay. Maybe this home. Yep. It's this. This is also a reporter, gymnasium. Okay. If nothing else, I'll continue sending some useful stuff to the group. But for now, that should be all, unless anyone has any other questions. Okay. You're welcome. You're welcome.